Yeah, thank you very much. Okay, yeah, thank you very much. Exactly. So, thanks for Mark, Astrid, and Aaron for inviting me to this nice seminar and to present my work. And of course, thanks also to my collaborators, Jan and Manuel, without whom this would have, of course, not been happened, because actually I'm a QCD person, and I'm now working in Gießen on hadron physics. But still, I thought, yeah, I think most of you know there is some appeal to work on quantum gravity, so I also wanted to work a bit on that. So yeah, and so I worked a lot during my PhD on spectral functions, and I also applied the methods I learned to quantum gravity now, during my PhD. Okay, I would like to. Okay, I would like to start by discussing a bit why I'm interested in real-time functional methods, or in general real-time physics and Lorentzian signature. Before I will briefly discuss the setup and the spectral functional methods that we are using, and the techniques. And then I will come to the actual results in gravity that we got. And I would like to briefly give, so for the brief overview on real-time physics. So why is this necessary or interesting? Well, physical particles and the things that we can do spectroscopy with are usually bound states. So like proton and the mesons, and sorry. So the masses and the properties of these bound states are usually located, or always located, on the Lorentzian or Minkowskian side of the theory. So what are bound states? Bound states are poles like of this form in correlation functions, for example, in a 4-point function. And these then we can write like this. And if we want to access these poles, they are always on the Minkowski side. We have to use real-time methods. And in gravity, there has been or there has been long-standing, for example, the suggestion to have geons, which are bound states of gravitons, very similar to the glue balls in QCD or Yang-Mills theory. And for recent hints on lattice, you can look at this paper here by Maas, Plätzer, and Pressler. And of course, also, if we look at scatterings and cross-sections, there are important questions for quantum gravity to address. For example, the question of unitarity. Can we have a unitary quantum theory of gravity? Then the question of causality, which is we always want our theories to be causal and to not have some non-causal instabilities. And eventually also experimental signatures, which can only be seen in experimental measurements, like cross-sections, for example. And here I would refer to a recent paper by Pastor Guterres, Jan Pawlowski, Manuel Reichert, and Giacomo Ruisi on the modification of lepton scattering due to graviton propagators. Okay, now what are actually spectral functional equations? Wait a second. Spectral functional equations. So first I would like to talk about the functional part of this title. And we use, like most of you maybe, use a path integral formulation where we couple a source to our fields to get a generating functional here. And then we usually work in the 1PI effective action formalism. And there are several equations on the market that we can choose of. And for example, there are Dyson-Schwinger equations, which I'm actually working now most of the time. And these can be considered to be quantum equations of motions. And there's of course the the functional renormalisation group, which is usually the tool that is used in quantum gravity, or in asymptotic safe quantum gravity, I have to say. And there you simply couple a regulator to your classical action, and you study how the theory changes if you vary this regulator function. And also in both of these approaches, there have been various real-time computations before, usually not with spectral functions, but also with. But then they're usually with contour deformations or with analytic continuations. And here are some for the Dijkstringer case, and here are some for the functional renormalization group case. Okay, having said this, I would like to turn to the spectral part of spectral functional equations. And here I show you a picture from Pestin Schröder, actually. And the whole idea of this approach is that the propagator is entirely determined by its discontinuities. So if you, for example, you might remember from quantum field theory lectures that the propagator has this Callan-Lehmann spectral representation here, which simply tells that the propagator, in this case of scalar particle, is simply given as the weighted integral over essentially ordinary Feynman propagators or classical propagators, and the weight that we have to use that stores all the non-perturbative information, and we call this the spectral function. And it is actually given by the discontinuities of the propagator, and I will show you in a second what this really means. So what can the spectral function have? For example, it can have one particle states, like a delta pole here. It can maybe include bound states if these states have overlap with the propagator you would, with the fundamental field you would like to have the propagator of. And then there are the two particle or n particle states rather, which have all the information of the scattering that one particle can have into further ones. And this is the main object we will work with later, and you will see why. So exactly, so the propagator is determined by discontinuities, and where causality comes into play is that if we want to have a causal theory, then our S matrix elements have to be analytic in the upper half plane. So if you want to, for example, look in p squared, then you should have no singularities away from this real axis. This is what tells you what causality means in my definition, or in the usual definition here. And in particular, there's one nice property. There's a symmetry, or rather a certain anti-symmetry between the retarded and advanced propagators. So this is this mirror symmetry here. And now, if you have a propagator at hand, you can always define your spectral function like this. So this is 2 times the imaginary part of the propagator in a certain limit. And why this is the certain limit, I will show you on this next slide. So here you see actually already pictures from our paper. So this is the graviton propagator at in the complex momentum plane. And here's the real part. Here's the imaginary part. And in both cases, I subtracted the trivial one particle pole at 0 because this would overshadow everything. And what we rather have here is a logarithmic divergence here at p equals 0. And most importantly, why I would like to show this here, you see that the imaginary part of this function features a cut. So you see, if you go with the real part here to 0, so here the axes are a bit, the axle labels are a bit unfortunate. But if you go from this side to towards real part of p equals 0, you get a different result as if you go from the other side. And this is a discontinuity and what we call a cut. And the difference of these two values is exactly the spectral function. Okay, so this was just to give some intuition and of the objects I would like to talk about. Now, how do we put them to use? So this is now the setup of really the spectral functional equations. And I would like to make a very simple example here in a scalar theory. And this is simply a polarization diagram. And so this is just a loop and the momentum integral over 2 propagators here. This is you can consider this a perturbative diagram or one that appears in a Dyson-Schwinger equation. In the flow equation, you would have another regulator insertion here, and then this would be G of Q squared instead. And for now, I would like to consider only constant vertices so that we don't have to look into this now, but you can also treat vertices in a spectral manner. And now the whole game is to replace all of these propagators here by their spectral representations, what gives you such a form. And here I already interchanged the order of integration. So usually the spectral integral would come inside the Q integral, and now I already switched them. And this is already non-trivial and requires a regularization of the integral, so that the integral has to exist and to be finite for this to be valid. And I will come to this in a second. But suppose we do this all consistently, and you can do this, then we get this form. And the green box here now is the whole momentum integral, and it's essentially a perturbative form. Well, the only difference is that these masses are actually the spectral parameters lambda 1 and lambda 2 here. And this you can integrate analytically, and you can use dimensional regularization, so you don't break any symmetries with the regularization here. And then all the non-perturbative information of this integral is stored in this spectral function integral here that is usually to be performed numerically. Okay. What is nice about this is, of course, that with this approach, we now have access to the full complex frequency plane because we can compute the p-dependence here analytically. But this comes at a price. For each correlation functions that we want to put in here, so we have additional spectral integrals. So as you can imagine, if you put in vertices, or you go to higher correlation functions where you get more and more propagators, the dimensionality of the system blows up, and this is what kills the numerics eventually. So this is as always, it's much simpler to work with this approach for lower order correlation functions. In addition, I mentioned this, that you have to do a spectral renormalisation for divergent diagrams. It is because you interchange the order of integration, not enough to simply, for example, drop the 1 over epsilon in this expression here. You can still get divergences when you integrate over these spectral parameters. So you also have to remove these divergences consistently. But you can do this. This can be done, for example, in a simple BPH set scheme, which will be natural actually to the flow equation that I will show you in a second. Okay, now are there any questions so far? So this was now essentially the conceptual thing. If there are anything that is unclear, maybe I can answer some questions now already. If not, I would simply go to the flow equation that we actually use. So as you all know, we can derive, or most of you know probably, we can derive the flow equation or the Wetterich equation by adding a regulator term to our action and then varying our theory with respect to this regulator. And in our setup, we choose a very peculiar one, namely just a Callan-Symanzik regulator, which is simply proportional to k squared. So this is the regulator scale, and there is really no momentum dependence in. And to explain a bit why we do this, I would like to consider the 3 different properties we would actually like to have from a regulator. So first of all, it would be nice to have Lorentz invariance, because if we don't have Lorentz invariance, the number of tensor structures in the system explodes, and we actually cannot work in Q squared or P squared anymore, but we have to separate vectorial and temporal directions. then we want to have causality. So this is actually crucial for our approach, as causality is a necessary condition to actually have a spectral representation. So without causality, our approach is screwed. And ideally, one would also have to have finiteness, so that the regulator function, as for example, the lithium regulator does, decays in the UV, or at least derivative decays in the UV, fast enough to make every flow equation you can build from it finite. Unfortunately, it turns out that there are relatively strong arguments that there is no regulator that can fulfill all three of these things. So it's not, there's no rigorous proof, but so far we don't know how we would construct such a thing. And this is why I put a question mark here. And the best thing that we can do at the moment is that we choose two of these three properties. And in order to have Lorentz invariance and causality, the only thing that you can essentially do is the Callan-Symanzik cutoff, where the regulator is only a k-squared. But then you lose something. You lose the finiteness of your flow equations, and you will have to have loops in your equation that are divergent. And you have to renormalize these loops. So you have to subtract the divergences. And you can actually do this in a consistent manner. And you can actually derive this renormalized CS equation. And here I put the full here just for notational reasons, because as you see, this looks a bit different than the usual flow equation. So this is the full 1pi effective action and not the average effective action. So as with the Callan-Symanzik cutoff, it does not really make sense to subtract the cutoff from the cutoff term from your action. So we keep it in. And this leaves us with this flow equation, where here this cutoff term is still inside of the trace. Okay, and now we also have this counter term, which makes the whole thing finite in a sense. But this is already not really true. This equation is finite from the beginning, but this dt SCT is fixed by renormalization conditions eventually. Okay, I don't want to go into details on this equation now, but there are a lot of discussions in gravity. For example, there's the first paper by Yannick Fähre, Jan and Manuel, of course, our paper. Then there is the derivation of the renormalized CS paper in this paper here, where we really show that the renormalized CS equation can be viewed as the limit of manifestly finite Wetterich flows. And at each step of this limit, the equation is finite. So there is really a consistent way to show how to get to this counter term without putting it in an ad hoc manner. And then there are, of course, applications, which are also very interesting, in my opinion. Yeah, if you have any questions, I'm also always happy to talk about this, but I think I would like to go to gravity now. And here I would like to first talk a bit about the object that we are working with. And this is the 2-point the flow equation of the 2-point function of the fluctuating graviton. And in particular, we want to talk about we only consider the flow of the traceless transverse mode of the graviton propagator, and this has this form here. And as it turns out, this flow equation has actually a superficial degree of divergence of 2, and this also doesn't change if you include non-perturbative effects, leading to 2 renormalization conditions, which you need in order to determine the counter term here, or the counter term flow, to say. And since we are using the spectral functional scheme, we have access to not only Euclidean momenta, but to the whole complex frequency plane, in particular also to the mass shell of our graviton propagator, we also choose to renormalize the graviton propagator on shell, meaning that our renormalization condition requires the graviton propagator to have a pole exactly at p squared equals minus k squared, where k squared is really the scale that is in our regulator. We can only do this like this because we set the cosmological constant to 0. But then we can do this. And we also require, this is the second condition we need, that the residue of our pole, of our graviton propagator, has unity residue. Okay, if we do this, we can also look at how this looks in the common parameterization of the graviton propagator. So you can always write the traceless transverse mode here as ZH of P times P squared plus K squared times 1 plus mu H. And this 1 plus mu H carries the deviation of the graviton mass to the K squared behavior here. And ZH of P carries on all the non-trivial momentum dependence besides of this. And what our parameterization now, what our on-shell renormalization condition now means is that mu of H is always identical to 0. And Z of H is, if you evaluate it on the pole, always equal to 1. Meaning that the on-shell anomalous dimension is also equal to 0 always. Okay, and there's actually, so you can either now put this renormalization conditions into your flow equation and determine the running of dt of your counter term flow and just implement it like this. But it actually is very convenient, since we have access to the full complex frequency plane, to implement the whole renormalization scheme with subtracted Kramers chronic relations. And if you are interested, I have a backup slide on this. Okay, now before I come to results, I would like to give you some idea about the setup and to discuss the truncation of our system. So if you look at the flow equation here, there are, of course, the graviton propagator going in, the ghost propagator going in, and of course, the different vertices. And what we use in our setup is the only fully non-perturbative thing is the resummation of the two-point function, and of course, a non-trivial Newton coupling. So this is everywhere where there's a green dot, we put in the full momentum dependence. And for all the red dots, we put in the classical ghost propagator, for example, and also the classical, or rather the Einstein-Hilbert vertices, but the only where there's only the running Newton coupling in. Now this truncation is actually closed if we include also a trajectory for the Newton coupling here. And I forgot to say, we work in the harmonic gauge, alpha equals beta equals 1, which is not so relevant now, but the beta function is actually not computed consistently with the Callan Symanzik equation, but we use an input from a 4D lithium regulator, where we modify the parameter such that we have the on-shell running of all parameters, meaning that eta h is equal to mu h is equal to 0, and then the Newton coupling, the beta function of the Newton coupling has actually, the dimensionless Newton coupling, of course, has a very simple form, which you can actually integrate analytically, and which gives rise to this, what is sometimes called the simplified trajectory. But in this case, due to our scheme, this is really the exact trajectory associated with it, with the on-shell fixed point, which is approximately 1.17. Here you see the dimensionless Newton coupling. So this is g of k as a function of k, all in units of the Planck mass. And you see, as usual in the IR, it is exactly k squared. And above the Planck mass, it goes into a constant with a fixed point value given below. Okay, so much to the setup. Now I'd like to show you some results. And I would like to start with a UV. Now, here I show you the spectral tail, and to see a bit what this is, I want to give you full parameterization of the spectral function here. So I told you that the spectral function can have poles and it can have cuts. So you have, for example, a one particle pole. And this one particle pole is in our scheme fully determined. So the residue is always one, so you don't see it set h here. And it's always at k squared. So this is why this is simply a delta function located with the argument lambda squared minus k squared. But now you can also have scatterings, and this is the really non-trivial part of this spectral function. And here I would like to show you how they arise. So if you look in textbooks, there are these notions of Katkowski cuts. And what these tell you is if you look at such a diagram, then you can see that, then you can automatically see that there will be a cut, so a discontinuity, which is associated with the decay of one particle to two, starting at the sum of all the masses of the lines you can cut with one cut, if you thereby split the diagram in two. So if you can make such a cut, you cannot really make any else. You can make such a cut for the graviton loop. You can make such a cut for the ghost loop. And in our case here, since we use a classical ghost propagator, where also the regulator is simply a k squared, also the ghost mass is at exactly k squared, meaning that both of these cuts in our setup will start at energy scales equal to 2 times the 2 times k, so 2 times the graviton mass or 2 times the ghost mass. Okay, and this is now what we get out if we compute this thing. So this is the spectral tail f of h evaluated at k equals 0. And this is here over lambda in max units of max Planck of the Planck mass, and actually it's the Planck mass to the power 1 and not minus 1. So the spectral tail has a rather simple form. It's constant in the IR, which is the logarithmic divergence at 0 that I showed you earlier. And it has a near quadratic decay in the UV. And actually, there's not so much happening everywhere else. And I would like to focus now on this near quadratic decay here, which goes like 1 over lambda squared log to the power 3 of lambda squared. And it is actually the spectral approach in combination with the asymptotically safe Newton coupling, which goes to a constant, which allows for an analytic solution of this spectral tail in the UV limit, independent whether you feedback the tail or not. And I also have a backup slide on this if you're more interested in this. So both the IR and the UV are essentially fixed. And what is crucial here in our setup is that the spectral function that we find is actually a spectral function that is normalizable. So the on-shell scheme leads to a normalizable spectral function, which is a bit of a surprise because earlier computations, so the one, for example, of Manuel, Jan, and Yannick Fähre, they saw a spectral function which was not normalizable. And also if you would make reconstructions of Euclidean momentum-dependent results, you would always see a non-normalizable spectral function, which is just due to the fact that you have a propagator that eventually goes with 1 over p to the power 1 plus eta, effectively goes with 1 over p, which cannot be associated with a normalizable spectral function anymore. However, we see this in our scheme, which tells that actually this on-shell scheme is essentially a consistent way of implementing a momentum-dependent and k-dependent rescaling of your fields. And we can also compute the norm of this spectral function. Let's call it z-spec by simply integrating over the whole spectral function, which gives us a 1 from the particle pole, plus the numerical value that we get when we integrate over the scattering tail. And this is approximately 1.45, which is not so relevant. But if we have this available, then we, in a very suggestive way, rescale the fields here and call this rho h physical by simply dividing by this norm, which is associated by rescaling the graviton fields at vanishing k, of course, by h mu nu over z to the power 1/2. To get a spectral sum rule, which is associated with an asymptotic state. And now I, of course, have to add that the state you create by acting with the graviton field onto the vacuum is not part of the physical Hilbert space. So this is not really an asymptotic state because it's gauge variant, for example. But still, it's very interesting that we can have such a thing, as it may be an interesting starting point for optimal or physical expansions. And we are still exploring this possibility. Okay, then I also have some interesting results in the IR, or rather we recover with the self-consistent treatment the universal logarithmic correction in the IR. So this is, in the IR, the graviton propagator is essentially given by the 1 over p squared, which is simply the one particle peak of the classical graviton. And you have a logarithmic correction, which essentially gives you exactly this constant behavior in the IR. Here is again the spectral tail f of h, but now not on a double logarithmic scale, but on a linear logarithmic scale. And here you see this constant behavior in the IR. So this goes up to 0, which is associated with this logarithmic cut. And the coefficient of this cut is actually scheme independent, but gauge dependent, and is in our gauge approximately 61 over 60 pi. And this was first computed by Kappa in 1980. And then the scheme independence, but gauge dependence was computed by Nano, then Spalowski, Manuel, Reichert in 2021. And so this prefactor is exactly the prefactor of this logarithmic divergence you see here in the real part of our graviton propagator. And now if you translate this to the spectral function, then this is exactly the 61 over 30 you see here in this inset here. Okay, there's actually a fun fact here. In the way I solved the flow equation, which is an iterative way, so we didn't solve the flow equation with a local time stepping, but rather we converted the flow equation to an integral equation and used a fixed point iteration in order to find a stable solution. You see that the process of converges very fast. So essentially, so the first iteration here is you just put in a classical spectral function, so classical propagators, and what you get out is essentially our tree improved one-loop perturbation theory. And then you put this back in on the right-hand side and you iterate, and you see essentially after 3 iterations, nothing changes visibly anymore. And then you iterate further and until your convergence criterion, your numerical convergence criterion is reached. And then you see that eventually nothing really changes anymore after 4 to 5 iterations. Okay. If you are interested in the iterative solution, I also have some backup slides on this. Okay, with this, I would already come to my summary. So I showed you how spectral functional methods work and how to use them to get access to the full complex frequency plane and how to get consistent analytic continuation of Euclidean field theory. There is one caveat, of course, for the flow equation. If you want to use this whole approach, you need causal flows, meaning you probably have to implement a Callan Symanzik regulator if you want to preserve causality and Lorentz invariance. What requires then eventually renormalisation of the flow equation. Okay, for gravity, I showed you the first self-consistent Lorentzian solution of the graviton propagator, so with fully converged momentum dependence. Then the onshore renormalization scheme that we chose lead to consistent momentum-dependent rescaling of the graviton field, which eventually led to a normalizable spectral function for the traceless transverse mode of the fluctuating graviton. Okay, so there are, of course, quite some open questions and some outlook. And the first thing is, of course, what happens when we upgrade the truncation? So it's not necessarily clear what happens when we also include the momentum dependence of the vertices, because as opposed to usual flow equations, the Callan-Symanzik flow is not as local in momentum space as it is for example for the lithium regulator, and momentum dependencies are important, and we will have to look and we want to look at also for higher vertex spectral functions, and this is work in progress with Gabriel Sant, Alvaro Pastor-Guterres, Jan Pawlowski, and Manuel Reichert. But if we also compute vertex spectral functions, we can of course also look if we see bound states like in Yang-Mills theory. So these are again the geons, or you can also call them prairie balls, analog to the glue balls. And then, of course, can we deduce implications for unitarity or of asymptotically safe quantum gravity by computing matrix elements? And also for this, we have to couple things to matter. And this is also work in progress with André Meissner and Jan Pawlowski. And with this, I would like to thank you.
Thank you, Jonas, for the nice talk.